mRNA, they are reading, then we see that there are two mRNAs actually represented by the ribosome. I mentioned last time that tRNA plays a central role in making sure that the correct amino acid is incorporated at the right time, and the mRNA is being read by ribosomes. And there are several mechanisms in place that assure this kind of fidelity that we need or desire actually to have functional biological products in the form of peptides or proteins then. So the tRNA here shown in green actually binds, let's say, on one side via hydrogen bonding to base triplets that encode the information for individual amino acid and brings in the amino acid that is bound on the other side, and we'll see how that works in a moment. So then, based on the genetic code that we discussed briefly last time, the appropriate amino acids will be incorporated. Okay, I also talked about the degeneracy of the genetic code, and the degeneracy is also it's based on the fact that we have often more than one amino acid, one and the same amino acid actually being encoded by more than one codon. And here we see also that the interaction between the codon base triplet that we find on the mRNA and this base triplet that corresponds to it on the tRNA, which we refer to as anticodon, is not always 100% specific. Okay, so a couple of things we want to see here, looking at this slide, is that we have three nucleotides on the mRNA, which goes from left to right in 5' end to the 3' end. And these three interact with corresponding nucleotides, or also a triplet actually in the anticodon, but the direction is opposite to the mRNA, meaning that our 5' end is towards this side and the 3' end is on this side. So this is also an anti-parallel interaction, just as we discussed it for the double-stranded DNA molecule. Okay, so here also we have anti-parallel interaction. So you can refer to this position here as position number 1 in the codon, but it would be the third nucleotide actually in the anticodon. Okay, so when you refer to positions, you want to make sure what you're actually referring to, the nucleotide in the codon or in the anticodon. Okay. We see here an example of the one codon interacting with its corresponding anticodon, complementary anticodon. But if we pay attention to this part of the slide, we see that there could be in the anticodon, actually in the first position of the anticodon, an unusual nucleotide, inosinate. Okay, remember the base is hyposensine, and we see that this hyposensine can actually interact with three different nucleotides, A, U, and C. Okay, so it was recognized actually by Francis Crick also that we have kind of quite a bit of flexibility in this position. So the first position in the anticodon and the third position in the codon respectively, depending in particular what kind of nucleotide we find there in the anticodon. Okay, so let's first take a look at this slide. We see that if in this position, the first position of the anticodon, we have a C or an A, the interaction is specific, so the complementary bases, namely a G or a U, respectively, will be bound. Okay, so if we have these two nucleotides, the C or the A, in this first position of the anticodon, only one codon will be recognized. Okay. If we have, and that depends, of course, also on the nature of X and Y here. Okay. But if we have a U or a G in this position, we see that we can actually bind two different nucleotides in each case. namely A or G or C or U. And if we have inosine, as we saw in previous slide, we can actually bind 3 different nucleotides in this position. So there's quite a bit of flexibility, and this was explained by Francis Crick with his so-called wobble hypothesis, which says that we have, particularly in this position, kind of a more flexible interaction, so it wobbles a little bit. Now, the rationale behind this, at least that's an attempt to explain why this interaction is not that specific and potentially not that strong also, is that it reduces the overall affinity between the codon and the anticodon. Okay, so why would you want that? Because it allows a faster protein synthesis if you can dissociate the codon from the anticodon more quickly. Okay, if you have a higher affinity between the codon and the anticodon, the off rate, pretty much, the dissociation rate at which the dissociation occurs might be too long, and this would significantly slow down the process of protein biosynthesis. So by making it a little bit less specific, we reduce the affinity and we can proceed actually with reading the mRNA and incorporating new building blocks into a growing polypeptide more quickly. Okay, so we talked about the genetic code, and often you read that the genetic code is universal, meaning that all organisms and everything that produces peptides and proteins actually uses exactly the same codons to encode for particular amino acids or for stop codons and things like this. This is not true. Okay, so strictly speaking, it's not true. In this table here, we see a couple of examples where codon usage, in particular in mitochondria of certain organisms, deviates from this normal code assignment. Okay, we see that in animal mitochondria, for example, even in vertebrates, this UGA is encoding information for tryptophan, is not used as a stop codon, and so on. Okay, so remember, mitochondria have their own DNA. They can also produce proteins. Okay, relatively limited number, but still, and they don't necessarily use exactly the same genetic code. Now, in order to justify the statement that I make in this class that strictly speaking the genetic code is not universal, I also looked for other examples and found a few. Now, this may not be particularly exciting, but still, I think it supports my argument that the genetic code is not really universal, because even outside of mitochondria, okay, we find a couple of organisms that use different codons to encode certain things. So in mycoplasma, for example, UGA is supposedly, okay, I'm not a microbiologist, used for tryptophan, and there are some ciliated protists that use these codons for glutamine. Okay, so remember that. Now at this point, we should take a closer look at the structure and function of tRNAs and how they are being charged with amino acids. So this is an example of a particular tRNA, namely that one that binds alanine, brings alanine actually to ribosomes in yeast. Okay, but overall, I told you that RNAs are historically or have historically been represented in 2 dimensions, and pretty much all these tRNAs, 2 dimensions drawn, actually have kind of a clover leaf structure. So remember the flower-like structure we discussed before for rRNA here. This has been described as a clover leaf, more appropriately, I guess. In 3 dimensions, it looks quite a bit different, more like an L. We have the anticodon, one end here, and both the 5' end and the 3' end on the other end. So there are certain regions that can be described and are characteristic for tRNAs, and I summarize them on the next slide, but just one word, based on the degeneracy of genetic code and the wobble hypothesis and things like this, you can calculate that it actually requires a minimum of 32 different tRNAs to encode all the 61 codons that encode for amino acids. Okay? In certain organisms we may have more, but at least it takes at least 32 tRNAs. So what are the general characteristics? And remember, okay, there are different tRNAs, different amino acids also, but they have some general features. So in length, they vary between 70 some, let me say, and 93 nucleotides. So we have a single-stranded molecule with a 5' end here, which actually is phosphorylated, okay, and a 3' end. We also see that we have quite a bit of self-complementarity to have this stem loop structure formed. I told you that the amino acid is actually bound here in this region where we have 5' end and 3' end, and there's a so-called amino acid arm, which contains 3 terminal nucleotides, namely C, C, and an A. Okay, so the very last nucleotide that we find here at the 3' end is an adenylate. And you want to keep that in mind because we will take a closer look at how amino acids are actually linked here to this adenylate in a moment. Then we have here in this region the acceptor stem, so-called acceptor stem, 7 base pairs between these self-complementary regions here. And then we extend here, coming from the 5' end, into another stem loop region, which has been called, or this loop here, or the stem loop region, has been called the D loop. And it has been called D loop because we find an unusual nitrogenous base here, namely dihydrouridine. We'll see the structure of this in a moment. So it's actually a reduced form of uracil. Okay. Then we also see here highlighted in red a couple other unusual nucleotides or nitrogenous bases. We see some methylated granulates here. Then we extend here, again going towards the 3' end, into a stem loop structure which has or contains the so-called anticodon loop, because here we find the anticodon, these 3 nucleotides, they can interact more or less specifically with the codon in this antiparallel manner, as I said. So we may or may not have an inosinate here, okay, but we also find some other unusual nucleotides here as we continue, a pseudouridine here, for example. Then here is a region that has been called variable loop because it's not found in all tRNAs. And then we come to another stem loop structure which can be called T-CG loop, okay? Because it has here a sequence that has a thymine, pseudouridine, we'll see in a moment what that looks like, a cytosine, and a guanine. Okay, sometimes it's only called T-CG loop, not T-CG loop. Okay, then we just continue towards our 3' end. So I already mentioned that tRNA usually contains a number of unusual bases or nucleotides. In the textbook you find a picture of some unusual nitrogenous bases, and supposedly you find all these in nature, in RNAs. I'm not so sure about this one, but I'm not an expert in this field, okay? But I just want to point out here a couple of methylated bases here, hydroxymethylated cytidine even, okay? Here is inosinate, or inosine, if we don't have a phosphate here. This one is a particularly interesting one, the pseudouridine that I mentioned a moment ago. What's so different about this here? What's so interesting about this? Nucleoside is shown here, nucleotide, if you phosphorylate it.
Isn't the ribose supposed to be the bottom nitrogen?
yes, we are actually supposed, let's say, supposed to have an N-glycosidic bond, so bond between the anomeric carbon of the ribose to this nitrogen number 1 here, okay, in uracil, but that's not the case. We've actually moved this here over to this carbon. Yes, and that's why it's called a pseudo-uridine. Okay. So again, when you think of nucleotides, don't just limit it to the 5 nitrogenous bases that you usually see in all textbooks and everyone knows and discusses. There are many more nucleotides that we find in nature, especially here in tRNA. We find a number of unusual nitrogenous bases. Good. So let's take a look at how amino acids are actually linked to tRNA, and they are linked by a class of enzymes called amino acid tRNA synthetases. It's quite a tongue twister, and these are highly specific enzymes that can recognize the appropriate amino acid as well as the corresponding tRNA specifically, and then form a covalent bond between the terminal adenylate and the tRNA and the amino acid. Okay, so the final product, let me see, the final product will look something like this. Here's a schematic representation of our tRNA. Then this here is actually the final adenylate that we had in our CCA terminus at the 3' end, okay, and here in red we see an amino acid linked to the 3' hydroxyl oxygen of this adenylate. So we have to form an ester bond here between the sugar here in the 3' position and the corresponding amino acid. So why am I pointing out here this particular adenylate? Because if you just go through this scheme here, it may be a little confusing, because what the enzymes do first is they activate the carboxy group of the amino acid, okay, to form this bond. Nothing's for free in life, okay, not even forming this bond and charging tRNAs with amino acids. It requires energy. So this carboxyl group needs to be activated, and it's activated by adenylating it. Okay, so you should know what this means. Now we link it to an adenosine monophosphate. How do we do that? Well, these little enzymes, they use ATP and they form a bond here between our carboxyl group and the first phosphorus of our previous ATP, so they cleave off pyrophosphate. Okay, and this pyrophosphate is cleaved into 2 inorganic phosphates. So actually, this formation of the bond here, a mixed anhydride, okay, costs us 2 ATP equivalents. And then we transfer the amino acid to the adenylate, okay, and there are 2 possibilities, just to confuse us a little. There are supposedly enzymes that directly transfer the amino acid to the 3' hydroxyl oxygen, okay, to form the final product. And then there are others that actually first link the amino acid to the 2' hydroxyl oxygen and then transfer it to the 3' hydroxyl oxygen to form the final product. Now, the reason why I say supposedly is I believe that this happens, but I don't quite think that the terminology is actually right here, because they distinguish these 2 pathways by saying that the enzymes that form the product directly, so linking the amino acid to the 3' hydroxyl oxygen, are class 2 amino acyl tRNA synthetase, and the other ones that first form the bond to the 2' hydroxyl oxygen are class 1 amino acyl tRNA synthetases. I think that this is not the right terminology here. I don't think that this is really the difference between class 1 and class 2 amino acid tRNA sensitivity. And the reason why I believe that is that I had a project a couple of years ago, and I had a student working on this, and we were supposed to, I wanted him to work with amino acid tRNA sensitivity, and he did some research, and found that this is not quite right, but it doesn't really matter, okay? So the final product is our amino acid linked to the 3' hydroxyl oxygen. Good, so I said that this charging of the correct tRNA with the correct corresponding amino acid needs to be specific, and for that reason, not only the amino acid has to be recognized specifically by the enzyme, shown here, the monomer, and here the dimeric one, so the different ones, monomeric and dimeric ones, but also the interaction between the enzyme and the tRNA needs to be specific. And here we see some pictures based on X-ray crystallographic studies that shows how tRNAs are bound by these enzymes. We also see the binding sites for the ATP here. Next slide, we see that there are even certain nucleotides that are specifically recognized by the amino acid tRNA synthetases in order to make sure that the correct tRNA is being recognized, and there are different colors used here for our tRNA in blue, and the orange ones are actually the ones that are recognized by the enzyme to bind particular tRNA specifically. And you find these, if I didn't post these pictures, you find them in your textbook. It's of the greatest interest. So let's take a look at the individual steps, individual stages or phases of polypeptide synthesis. And again, I want to remind you that the peptide or product is synthesized starting with the amino terminus and proceeding towards the carboxy terminus. And I pointed out that this is a non-trivial task. Okay, so it's actually quite elegant how this is being done, and we in the lab, we can't really do this reliably. I also mentioned that ribosomes read the mRNA 5' to 3' direction, and we saw that translation occurs in polyribosomes. Remember these little mice we saw last time. And I told you that the chain elongation, okay, so if we bring in a new amino acid building block to a nascent chain, occurs by the linkage of the growing polypeptide to the incoming tRNA's amino acid residue. So this is a lengthy description of something that is actually quite simple, and is shown on the next slide. It shows that, first of all, we have several different sites in the ribosome that we can distinguish. Actually 3 shown here, only 2, namely the A site, the P site, and then an exit site or E site, which we will see on subsequent pictures. We'll see that the very first amino acid actually that is bound by ribosomes will be bound here. You see this in this picture here, will be bound to the P side, okay? But then a new incoming for peptidyl site. But then in subsequent reactions, the next amino acid will be bound to the A side. So we will have our peptide first at this position when a new amino acid comes in, and then at this point still the peptide and the new amino acid are bound to their tRNA. So this would be the last tRNA at this point, and this is the next one carrying the appropriate amino acid. And what happens then is that we form our peptide bond by transferring the growing peptide over from the P side to the A side. Okay, so we have a nucleophilic attack here of this nitrogen into this carboxyl carbon, and form a peptide that at this point resides in the A side for a while, for a moment I should say, and the peptide has grown by one monomeric building block. So the catalytic activity here resides in the 23S rRNA, so it's not in a protein component of ribosomes. And I mentioned this previously. Nowadays we know this and we simply accept this, but this is just another example something where people or scientists believed for many, many years, forever pretty much, that this catalytic activity for sure resides in a protein component, because we were just so used to proteins being the primary enzymes. Okay, but here we have an enzymatic activity coming from an rRNA actually, and this was elucidated only maybe 2 decades ago. So. I told you previously that all polymerization processes can be broken down into 3 stages. We'll see later again, and I mentioned this already, that for protein synthesis we can include 2 more, but for the time being, let's just focus on the initiation, elongation, termination, just as we discussed it also for transcription. So the initiation phase describes, as you may remember, the parameters or criteria, factors that are required to assemble the polymerization machinery. In this case, it describes how ribosomes bind to mRNA, how they bind the first tRNA. So I talked about differences between prokaryotic and eukaryotic organisms as it comes to recognizing the starting point for translation. I said that for eukaryotic organisms, this 5' cap is of particular importance in mRNA, and I mentioned at that time already that for prokaryotic organisms, so for bacteria, we have upstream of our initiation codon actually nucleotides that can base pair with a corresponding sequence in rRNA. In particular, it's the 16S rRNA towards its 3' end, and we see that upstream of the initiation codon in mRNAs, we have here highlighted in orange relatively short purine-rich sequences through which the mRNA can interact with this 3' end of the 16S rRNA. And these sequences here that serve for correctly positioning the mRNA in the ribosome are called Shine-Dalgarno sequences. Okay. The first codon that is being read by ribosomes is AUG. I mentioned this last time when we talked about the genetic code. And the first amino acid to be incorporated is actually a formulated methionine. Okay, so we have a formyl group here, aldehyde functionality, that is linked to the alpha amino nitrogen of methionine to form an N-formyl methionine. And this is, in bacteria, always the first amino acid that we find in polypeptides to be incorporated, let's say. And the formyl group here, that's not surprising, actually stems from a tetrahydrofolate, N10 formyl tetrahydrofolate. So remember the different types of tetrahydrofolate derivatives. This is one important role that these have here to actually find this formulated methionine. If you remember the genetic code, AUG is actually not only used as an initiation codon or start codon, where here N-formyl methionine is incorporated, but it's later also, later means in other positions within a polypeptide used to incorporate methionine. However, at the start codon, only a particular tRNA can actually bind to the ribosome, and it's the one that brings in N-formyl methionine. Okay. And later then, the other tRNAs that actually bring in methionine can bind. But at the initiation phase, it's only this particular tRNA that has been loaded with N-formyl methionine. So, on this slide we see what happens actually during initiation, and we see that it's a little bit more complex than just having the ribosome, let's say the assembled ribosome, bind to mRNA and then bind to tRNAs, because this process and also subsequent processes, elongation, termination, actually require a bunch of proteins called factors. Okay, factors is another term that has been used or is being used in biochemistry to describe something that plays a certain role in a process. And usually when we call something factor, by the time we call it or name it factor, we don't necessarily know really what it does and what it is. Okay, so we need a number of factors. Actually, we need initiation factors, we need elongation factors, we need release factors, or being proteins that play a role in polypeptide synthesis or protein synthesis. And then we'll see, and we see this already here, that these processes, these individual steps, I should say, also require quite a bit of energy. We saw that just loading a tRNA with an amino acid requires 2 ATP equivalents. Okay, and then we see here that we actually also utilize in the initiation phase already an ATP equivalent in the form of a GTP. Okay, I'll tell you a little story in a moment, but let's first take a look at the initiation. So what happens first is that the 30S, so the small subunit, actually interacts with initiation factors here, 1 and 3, and binds to an mRNA. Okay, so it's not the assembled 70S ribosome that binds the mRNA, but first the small subunit, with the help of these initiation factors, actually binds the mRNA. Then this so-called 30S initiation complex binds our first tRNA. It's the one that brings an N-formylmethionine. But we see that this N-formylmethionine actually is bound with the help of another initiation factor 2, that is bound to GTP. Okay. Now to this complex here of the small subunit, these initiation factors, the mRNA and of N-formulated methionine tRNA, binds the 50S subunit. Okay. And GTP is hydrolyzed to GDP, so we actually consume 1 ATP equivalent here. And these initiation factors 1, 2, and 3 actually dissociate. And this forms then the initiation complex. Okay, so this is the initiation. Then based on the genetic code, took this out I guess, next tRNA is being bound. We have our specific, more or less specific